Welcome! In this series of short videos, we will look at topics common to both the PowerBasic console and Windows compilers. Today, we will look at the searching of arrays. Following the recent videos on machine learning, there are probably some questions on array searching. So that's what we're going to be looking at today. Holding data in arrays is a very useful and efficient way of actually holding data within memory so it can be searched easily and quickly. In order to determine whether the data you're looking for is within an array, you can use a number of different search methods. So first of all today, we're going to prepare an array with some data so we can search it. So what we have done here is we have dimensioned an array of string values, holding 20 elements from element 1 to element 20. And we're going to populate this array with a function called populateArray. We're passing a single parameter to this new function, which is a reference of our array itself. Arrays, of course, can take data from many sources. But today we're just going to directly populate the array using the arrayAssign command. So in the parameters list of this new function, we have a reference to the array we wish to populate. And as you can see, this is a string array. We are performing this population using the arrayAssign command. The arrayAssign command has two parts. The first part is the name of the array we wish to populate, followed by the equal sign. And I've folded each of the lines of data down to a separate line so it's easier to read. But it's basically a long list of parameters. And each of these parameters we are supplying has 3 words. The first one is we won't look. When you use the arrayAssign command, it takes the first parameter, in this case we won't look, and populates it into the first element of the array you have designated. It then continues to populate each of the remaining elements with the values you have assigned. So we have populated this str data array with 20 values, each of them a string. What we're going to do next is we're going to look at how we can search out the information from this array. And in order to determine which is the best method of searching, we're going to do some metrics on this. So first of all, we're going to set up the search criteria. We're going to be looking for the words we will in this array, and we want to return how many matches we've actually found. As we can see from the array data that we have just populated, there are a number of matches which will obviously come up. For example, we will see, we will return. When you're searching string arrays, you can either do a case-independent search or a case-dependent search. If we were looking for a case-dependent search, then this element of the data would not be returned, because the first letter is uppercase W. So we're going to look at 2 methods of searching data out of this array. The first is going to use a for next loop. And we're going to insert that code into a function called searchForData, passing 2 parameters. The first being our search criteria, what we're looking for, and the second being a reference to the array itself. In order to determine how many matches we have, we're going to return from this function a value which is a long. This will be the number of matches. So we'll declare this local variable as a long above the call to search for data. Before we write the code in this search for data, we'll want to work out how long it takes to actually run this function. PowerBasic has an inbuilt command called ticks. Ticks is a very useful command in that it measures clock cycles of the CPU. So you can get a very granular value back for how long your code took to run. So we'll declare a local variable called cycles as a quad. A quad is one of the variable types which can contain very large numbers indeed. And the command to start counting is ticks, followed by the variable into which you wish to put the value. And after the function has completed, we will use the ticksEnd command, followed by the variable into which we've been putting our cycle count. As the Windows operating system is a multitasking system, it's always possible that the number of cycles will vary between runs. So we're going to run a loop. This loop will call our search for data function many times, and it will take the average number of cycles to work out how long the function takes to run. This should give us a much better average of the time it takes to run our function. So we'll create two variables to enable that, one for our loop and one for a loop count. And we will set our loop count at a value of 50,000. So it's going to call our search for data function 50,000 times. And after the function is completed and we have closed off the ticks command, we can then display on screen the number of matches found and the number of search cycles we have actually used up as an average. We can do this using our funlog command, which will just push the information out to the log. We're first of all displaying the number of cycles divided by the loop count. This will give us the average value. And we'll follow that with the number of matches of data we've actually found within our array. So let's go now and create this search for data function as a for next loop. So here is the skeleton of our new function, search for data, with its two parameters. The first being the search criteria, what we're looking for, and the second is a reference to the array which we wish to search. As we're going to do this in a for next loop, we need a row counter, and we'll have a variable for the number of matches we've actually found. So our for next loop is going from row 1 to the upper bounding of the array, which will be the last element in the array, which will be element number 20. We then have to test to see if the value passed in on the parameters, the search criteria, matches the data in the array. So we will first look for a direct match. We can do this with a simple if condition. If the element long row in our array matches the search criteria, then we will increment the matches variable. And at the end of reading through each element of the array, we will return the value to the calling function as long matches. So our search criteria at the moment are the words "we will." If we run our application now, we will see the number of matches found is 0, none at all. However, the search cycles are 1,727. So stepping through each element of the array took around 1,700 CPU cycles. So let's now search for something we know that will exist in the array. If we look for the very last entry in the array, and we change our search criteria to match that, and run the application again, we're taking 1,950 search cycles now, and it has returned one match. So we can take this as our baseline for this for next loop. So that's if it's a direct match we're looking for. If we're looking for a partial match, we'll need to use a different command. So now we're using the in-string value. This looks inside the element of the array and looks to see if part of the data within that array matches what we've passed in on that criteria. So if we're looking for the words "we will," and we run the application again now, we'll see we found 13 matches. And the search cycles are much the same value, 1,763. This search is a case-dependent search. If we want to make it case-independent, we need a different if statement. This statement is using the uppercase command, $. Applying this to both sides of the if statement means it's going to be a case-independent search. And we're using the left $ command to look at the beginning of the string in the array. So we're interested in the length of the search criteria, in other words, the words "we will," and we're looking for this to exist at the beginning of the data in the array. If we run this now, it will return 13 values and runs in around 12,000 CPU cycles. So that's basically our baseline for next loops. We're now going to create a second function which is going to use the array scan function within PowerBasic. And we're going to use this in exactly the same way. We're going to use the ticks command to measure the clock cycles, we're going to do a loop for the same number of iterations. We're going to call a new function called scan for data, again passing two parameters, the search criteria and the data array itself. And once this has completed the loop, we're going to use text_end to close off our measurement of the clock cycles. We will then print out the number of cycles and the number of matches we have found. So let's now create this new scan for data function. So here is the skeleton of our new function, as before with two parameters, the search criteria and the reference to the array itself. We're now going to use the array scan command, which is inbuilt to PowerBasic. The first parameter on array scan is the name of the array which you wish to scan, in this case str_data. The next part we're going to use is the from statement. This tells the scan that we're interested in from characters 1 to the length of the search criteria. In much the same way we used the left dollar command in the previous function. We follow this with a collate command, which is saying collate uppercase. So this is a case-independent search. And we're looking for it to be equal to our search criteria. And the final parameter is toLongMatch. This returns the element number of the array in which we found our match. And if we find the match, the value in longMatch will be greater than 0. So we're going to increment the longMatches variable to record that we have indeed found a match. And we will return that to the calling function. The array scan command will only find the very first match on our search criteria. It will not search through the rest of the array. But let's run that now to make sure it will return a value. And there we have our scan cycles are showing as 1125 to find the first match. But we need to scan the rest of the array to see if there are any more matches, because we know using our for next loop that it did indeed find 13 matches. So how can we use the array scan command to scan the rest of the array? Since the longMatch returns the element in which we actually found a match, we can then advance to move on to the next match. So we're going to use a variable called nextMatch to do that. And we're going to run this in a loop until we find no more matches. So we can again use the array scan command almost exactly the same way. The only difference being that after the name of the array where we had two brackets, open and close brackets, we now have a variable in there. This is telling array scan to start its scan at the next element along, because we've taken the match variable and added 1 to it. The rest of the command is exactly the same, and it will return the match it finds in the longMatch variable. And if the value returned in match is greater than 0, then we did indeed find a match, so we can then increment the matches variable. We now need to move on to the next slot to start searching again. And we need to change the value of nextMatch to tell the array scan where to start looking from. So we're taking nextMatch and adding on longMatch to it. The reason for this is that the array scan command starts its scan from the element of the array we told it to start at. If we told it to start at element 5 and it found a match at the 7th element, the value populated into longMatch would be the value 2, because it's 2 elements beyond where it started. So we need to calculate the next match based on that criteria by adding on longMatch to the value in nextMatch. So if we run this code now, it should run round this loop and scan the array for every match it finds. And there we have it. We're getting the same results back from both functions. The for next loop is taking just over 12,000 CPU cycles to return 13 matches, and our array scan is taking 15,000 cycles and giving us again 13 matches. So at first glance here, it would appear that the for next loop appears to be slightly more efficient than the array scan. And remember, we're actually running each of these functions 50,000 times. This works on the assumption that the data within our array is fairly random. and both functions will need to look through every element within the array to see if there is indeed a match. However, what if the data within the array was unique for each element? And we want to find this element here, prepare to see, which is fairly close to the beginning of the array. If we run the code now looking for this, we will see something quite interesting. The number of search cycles for the for next loop is around 14,000. However, the number of cycles for the scanning method using array scan is only 2,700. Let's run that again to make sure that just wasn't a fluke. And we're getting very similar data coming back. So what makes the array scan suddenly much more efficient than the for next loop, despite us having not changed any code? Let's try one further code change to see if it makes a difference. Since we know we're only going to get one value back from this particular search, let's change the for next loop so that when it does actually find a match in the for next loop, we exit out of the loop. We can do that using the exit for command, so that once we find a match, we exit immediately and return to the calling function. If we run this now, we'll see we have significantly reduced the number of clock cycles for the for next loop. It's now down to 5,000. However, the array scan command still beats it at only 2,700 cycles. So when it comes to which type of search is the most efficient for your data, it does really depend on what you're looking for and what's in the data. But this method of actually using the ticks command to work out how many clock cycles parts of your application are using when you're developing it is very useful. Because if you are calling a function many thousands of times, the faster the function runs, the better for your application. And once you have optimized your code, you can then just comment out the ticks commands. Hopefully this approach to array searching has given you food for thought. But that's it for today. Thank you for watching.